So today we're going to be talking about and really something very related to design of experiments, but with a slightly different objective. So when we talk about design of experiments, we are discussing how does one or several quantities of interest depend on the input variables, uh, the control factors we can influence or we can change. Optimization is something very similar, except for that we are looking for how does the output depend on the control factors, and with the intent of changing the control factors to maximize or minimize the outcome. Let me give you some examples in aerodynamics. So for example, if we want to design an airfoil and we want to maximize the amount of lift that can be generated by the airfoil. Okay, so that's basically looking at CL max. CL is the lift coefficient, right? The amount of lift non-dimensionalized by the aerodynamic pressure, and again non-dimensionalized by the area of the airfoil. Then what happens is that on the different Reynolds numbers, on the different basically non-dimensionalized velocity that you are encountering, the airfoil you can optimize looks something like this. When the Reynolds number is 1,000, you have a very thin and relatively flat airfoil. When the Reynolds number is 10 times larger, it doesn't really change that much. And if you look at these airfoil shapes, it looks actually remarkably similar to the kind of wings you expect on an insect, right? On a large insect. And that's exactly the kind of Reynolds numbers they are flying at. Now, if you look at slightly higher Reynolds numbers, the kind of Reynolds numbers you expect on birds, what you see is a significantly more curved airfoil. And as you increase the Reynolds number larger and larger, the curvature seems to increase, and you get thicker airfoils. So this kind of optimization is what we are typically doing in a lot of engineering applications, right? So in this case, the factors you want to control actually include a lot of things. It include, for example, the thickness of the airfoil as a distribution, right? I mean, you probably have to specify not one thickness, but a collection of thicknesses, something like 20 different thicknesses at different X locations. You also have to specify camber in a similar way, right? The camber is specified as basically a different Y locations of the center line at different X locations. So you probably have on the order of a few dozen of control parameters you want to vary to figure out how to maximize a single thing. In this case, the maximum lift coefficient. Another example is, what if you don't want to maximize the lift coefficient, but you want to maximize the lift over drag ratio, or the L over D, right? So that's a parameter that controls the glide ratio, for example, if you build an airplane out of this airfoil. In this case, well, the design variables or the control variables, the control factors, are exactly the same, the camber and thickness of the airfoil. But in this case, we have a different objective function, right? We need to compute the lift and also the drag. So in this case, we get significantly different airfoil shapes. Okay. Again, when the Reynolds number is small, you get these very flat, very thin airfoils. As the Reynolds number increases, you get airfoils that looks a little bit more like the kind of airfoils you expect on airplane wings. So these are the non-obvious examples of design optimization. So that's the kind of things we are talking about today. So let's first of all write down mathematically what is a design optimization doing? So a design and optimization, just like control variables, just like a design of experiments, deals with an objective function, one or more objective functions. We write it as a J. In this case, in design of experiments, we call this output as effects. In design optimization, we call this J as objective functions. So in the case we are looking at, the objective function is the maximum lift over drag. Okay, and S are the inputs. So this is the output. J is the output. So S is the input. They call the design variables. And in design of experiments, this is called the control factors, things you can control. These are the inputs. Okay. So how the objective function depend on the design variables. So usually the objective function is most often one or a small number of outputs. And the design variables in a typical optimization is more numerous than the objective functions. So for example, in this airfoil design case, the design variables has a few dozen dimensions, right, usually. And things get even more complex if you're designing a wing as opposed to an airfoil, right? Then the number of design variables can easily become more than 100. But still, you are looking at a few objective functions like maximum lift coefficient or L over D. All right. So, and usually, how do we compute J as a function for S? Is a given model. So basically, we need to figure out what model we should use, right? In aerodynamics, we may use thin airfoil theory, right? If we care about, for example, the drag in a subsonic case, then thin airfoil theory doesn't work as well because it doesn't give us the drag. So we have to use more sophisticated models, sometimes a computational fluid dynamics model. But a given model that computes J for any S. Okay. All right. So the optimization is usually given as a maximization or minimization over S as being the parameter space of J of S. So this is an optimization problem. So today we're going to focus on how to solve optimization problems like this. Okay, so we're just giving you the really a very simplistic overview of optimization methods, and we're going to be starting from the simplest, easiest to solve optimization problems, and stepping towards the more complex ones.